Okay, and now you're headed to the last lecture of the series by Vladimir Dotsenko.
All right, let me say a few words how to check this condition that the relations form a Grobner basis, because whether it is, well, I made this warning that it's not fully general, but still it's a useful criterion, so let me say how to check that. So in general, what I just erased actually, so the definition of a Grobner basis say that, so definition of a Grobner basis requires that all non-simplifiable monomials form a basis. And this is not, so I told you that that checking it is an easy task. Checking the definition directly is not an easy task, because generally algebra is infinite dimensional, so you need to check a bit too much. You have an infinite task to accomplish. However, there is a useful result, which is called the diamond lemma, which well, it's more general, but I'm talking about only quadratic relations, so I'm going to state a particular case of a more general result, that it is enough to check that the non-simplifiable monomials of length 3 form basis among non-simplifiable monomials of length 3. So you really only care, so if your relations are quadratic, then whatever bad happens, you already see on the level of cubic terms. So I'm not going to prove this result. It's, as I said, a particular case of this general result called the diamond lemma criterion for Grobner basis, which appears in many different sources, but let me rather say, let me rather give you an example which will so it's not, so the example I'm going to give, it's not completely honest example, because I'm going to write relations which have quadratic and linear terms, but nevertheless I will, it will be, except for that, I think it's a very useful, very good example. And it also will explain the words, the abbreviation PBW here. So let's take generators x1, xn, and relations xi xj minus xj xi is equal to the sum ofCijk xk. So relations that say that commutators can be written as linear combinations of generators. And let us understand what are the hidden consequences of these relations. So these relations, they kind of say that generators commute modular the linear terms. So let's say we can say that this guy, in each relation we need to choose someone. Let's choose the leading monomial like this, xi xj, where I is bigger than j. And so remember the example that I was showing before with xy equals to 1, yz equal to 1. So what are the hidden relations that we may possibly miss? So what we need to do, we need to take xi, xj, xk, where I is bigger than j, bigger than k. And then we can rewrite it in two different ways, right? So we can rewrite it as xj, xi, xk plus lower terms, or xi, xk, xj plus lower terms. So this guy, so what can we do here? We still, I is bigger than k, so now we can exchange xi and xk. So it will be xj, xk, xi plus lower terms. And here there will be, we have xi and xk, so this we can write it as k, xk, xi, xj plus lower terms. And now we can exchange xi and xj here. We can exchange xj and xk here. We get the same. So we arrive at in the same way. We arrive in both situations to xi, xk, xj, xi plus lower terms. So everything seems good except for the lower terms from here, and the lower terms from here are different lower terms a priori. And that's how hidden relations appear, right? So we might get a contradiction, that unforeseen contradiction. And the exercise, and that exercise has a completely different status from the exercise from the previous lecture. This is a learning exercise that I encourage everyone to do, is to check what happens, what kind of lower terms you get, what they write into. And so the exercise is that there are no hidden relations if and only if Ci, Jk are structure constants of Lie algebra. So if the Jacobi identity, so if you view this as the bracket of xi with xj, and so it structure constant of Lie algebra means that they satisfy some quadratic relation saying that the Jacobi identity is satisfied. And that explains you the PBW, because so this means that if Ci-Jk are structure constants of Lie algebra, there are no hidden relations. Our relations form a Grobner basis, and the non-simplifiable monomials are just look like just commutative monomials in the letters x, and this reproves for us the Poincaré-Birkhoff-Witt theorem that says that the universal enveloping algebra looks like the polynomial algebra as a vector space. So that's a very instructional example of what exactly happens. Yes?
Saying there's no hidden relations means that the non-simplifiable monomials are linearly independent? Is that the...
What I mean, okay, so let me let me say the following, that there are several different ways to check that non-simplifiable monomials form a basis. So, in principle, the algorithmic way, the way you can easily teach a computer to do, is as follows. You look at the leading terms of your relations, you look at possible overlaps of those leading terms, so monomials of length 3, which begin with a leading term and end with a leading term. You rewrite it in different ways, and then you try to reduce it using to simplify it. And your goal is to arrive at the same result on both sides. If for each such pair, you arrive at the same result, you are in luck. If in one of these situations you didn't, then there is a problem. So that's a completely algorithmic criterion. Right. So now,
don't erase anything on the left.
Yes, nothing on the left, on the right. The next thing that I want to say is that a little result. Well, I keep naming all these as facts, so let me call this fact also, because in fairness I will give a sketch of proof but not the full proof of it. So if Q is a quiver with one vertex, the PPW basis criterion for Koszulness applies. Well, one vertex and any number of loops. More generally, there is a class of quivers for which it works, but it's not a very big class. So if Q is such that so for the incidence matrix, Mij is just constant for I different from J, and on the diagonal each element is equal to C or C plus 1 for all I and for some C, then the PBW basis criterion applies. In general, for other quivers, it is not so a precise statement is that it is not clear. So for some obvious choices, for choices of order, so it all depends on the choice of ordering of monomials. For the choice of the ordering that works here, for other quivers it doesn't work. So it really, but in principle there is a continuum of different orderings to choose from. So it's yeah. So in general, it is an open question if one can find a suitable, a good order. Now, so let me let me focus on the two-vertex quiver because it's already sufficiently instructional. So here we have, so there are two loops, so we have even generators, generators A0, A1, and so on, which commute and they satisfy the, so a priori they satisfy the condition that A of z is equal to 0 and A of z, A prime of z is equal to 0. But it so happens that the first relation implies the second if you just take the derivative. So you just have the relation A of z square is equal to 0. So A0 square is 0, A0, A1 is 0, A0, A2, well, let me write it. Yeah, well, to be systematic, let me perhaps write it like that. And so I'm going to say that the bigger I, the bigger the generator AI is. So the presence of A0, for example, makes this one smaller. So here the leading term is A1 square, here the leading term is A1, A2, and so on. So what are the normal, non-simplifiable monomials? The non-simplifiable monomials, so if you look at this, so here, well, there is just one term who is leading term A0 square, here A0, A1, here A1 square, A1, A2, so the leading monomials are AI square and AI I plus 1 for, well, I keep using I for the vertices of the quiver, so let me perhaps AK plus 1. So, so these are the leading monomials. So the non-simplifiable monomials are monomials where there are no squares and no consecutive guys. So where things go with gap at least 2. And it is very easy to write down the generating function for dimensions of this because, you know, if you have things that go with gap at least 2, you subtract 2 from the second, 4 from the third, and so on, and they collapse to just anything. And once you do, so this is, there is some kind of easy, I suppose, bosonic formula for the for this kind of thing, and then what happens is that you know we discussed what the linear dual of the algebra AQ is in the previous lecture. The linear dual are symmetric polynomials multiplied by this kind of generalized van der Waals. And so you can compute character on that side, and you immediately see that the dimension of the space of cubic elements is exactly what non-simplifiable monomials predict, so there can be no bad surprises because of that. So you can compute the dimensions of homogeneous components of the space of cubic elements and see that it coincides with the prediction given by non-simplifiable monomials. So non-simplifiable monomials, they always span the algebra. The fight is to determining whether or not they form a basis. And so if the prediction if the two estimates coincide, if the prediction coincides with the actual dimension, then we can stop here. Everything is fine. Okay. So now, and at that, yes, what do I want to, how do I want to structure the rest of the lecture? I guess at this point, it is really necessary to say why on earth we've been talking about these algebras, how is this story related to DT invariance? Yes?
Can I use this Grosvenor basis to read the character? This is what you mentioned, right?
Yes.
But how to read bosonic character?
Well, what I mean is that if you fix the length of the monomial, for example, you look at the cubic terms, then you have sort of a bosonic formula for this, because you have non-simplifiable monomials AI, AJ, AK, where where J is greater than or equal to I plus 2 and K greater than or equal to J plus 2. And then if you do the shift, you just have the, up to a shift, it's partitioned into 3 parts. So yeah. You have the, you get Q to some power divided by 1 minus Q, 1 minus Q squared, 1 minus Q cubed. So this is, I mean, yeah. This is what I mean.
So there is some mention over this after all.
So I just fix the length. So then if you want the whole algebra, you will take the sum over all lengths. But since we only want to check the criterion of diamond lemma, we just look at the cubic terms. Okay. So the functional realization of the linear dual of AQ tells me of AQD, if you want, tells me that, so what was it? It was some product of differences times the these multisymmetric polynomials. So the character, the generating function for dimensions of homogeneous components for multisymmetric polynomials, it has its own bosonic formula, and so we will get the character Q to some power, some Q numbers that maybe I'm not going to write precisely. And so then, of course, what happens here is that this guy is going to be this character is going to be a formal power series in Q. So for a, well, perhaps since we dualized, perhaps rather in Q inverse, well, depending on the conventions. But the point is that in our algebra AQ, we had these generators AIK of degree MII plus 2k, so all the degrees were non-negative, so all this algebra was concentrated in non-negative degrees, and it's linear dual, maybe if we use appropriate convention, in non-positive degrees, but in any case, degrees of the same sign. So this character will be an honest power series, perhaps in Q inverse, depending on your convention. Then there is also the motivic generating series of Q, so the generating function for homogeneous components of the homological whole algebra. And at the first glance, it is of different nature. It is a Laurent series. It has some, again, depending on the conventions, either Q or Q inverse appears sort of in finite part and the other in infinite part. So somehow it's a little bit bizarre to try to compare the two because those are things of different nature, apparently. But now, let us approach it, let us forget about all this and approach it in a sort of very hardcore algebraic way, because after all, the way that this formula is written, it's a rational function in Q, right? And for the homological whole algebra, it also happens to be a rational function. And then you examine it carefully and you find a very you find that they more or less if you view these as rational functions, then everything is fine. They more or less coincide. So what happens is that the Poincare series of the algebra AQ. So this the variable x. So here we have x1, xm, where m is the number of vertices, so this accounts to that multigrading by vertices of the quiver. This accounts for homological degree. Let me see to give you the correct statement. So for one of the standard conventions, if you rescale x by q to the power 1/2, this is precisely what is, well, the Poincare series of the homological whole algebra. So I mean, I use AQ for the algebra, so I'm a little bit hesitant to use AQ also for the motivic generating series, so I won't. It's a little bit easier in papers where you can use A in different fonts, but on the blackboard, the difference between different fonts is a little bit more elusive, so let's not do it. Right. So then somehow, so what I'm saying is that the functional realization of the linear dual vector space gives this insight that the two things are very closely related. Then, we want to, in computing the DT invariants, we would like to represent this as the platistic exponential of something. Then we would like to see that something is actually equal to 1 minus q, perhaps, times something else, and that something else is responsible for the dt invariance. So somehow, so this corresponds to the fact that we already talked about yesterday at some point, that for a symmetric quiver, so the conjecture of Kontsevich-Soibelman proved by Yefimov says that the homological whole algebra is a free supercommutative algebra. Its generators come in these chains, or infinite chains, so hence 1 minus q here, and so the part, so if you take the beginnings of all chains, this is precisely what kind of categorifies, in a sense, the dt invariance. Now, what happens here? The algebra AQ, by its construction, it's very much non-free, right? It has generators and quadratic relations, and you cannot get away from it. But somehow its Koszul dual algebra, it's the universal enveloping of Lie superalgebra, so as a vector space it looks like the symmetric algebra of something. So if we could somehow relate to it to the Poincare series of AQ dual, we would be in luck, right? Because then we know how to write it as platistic exponential. We need to take precisely that Lie superalgebra that we are considering. Because so this is the platistic exponential of the Poincare series of GQ. And in fact, we are in luck because so if AQ is Koszul, then there is a magical formula. It's not so magical, I will explain to you immediately. So there is exactly the appropriate little shift. And the product is equal to 1. And essentially, this magical formula, it's just the Euler characteristics of the Koszul complex. So it's not very magical. It's something that we know. And the fact that you have q to 1/2 here rescaling, this just corresponds to what I mentioned several times yesterday and today, that under Koszul duality, parity changes, so there is this little shift that is going on. Yes, and so this is actually, so under the assumption of Koszulness is just equal this -1. And in the platistic exponential, we can just insert minus sign here, which shouldn't really bother us because what's little minus sign? And so essentially we have the two platistic exponentials, and so we see that we need to multiply by 1 minus q the character of GQ, and this will more or less give us the dt invariance. Now, how do I make use of the remaining 10 minutes that I have? I'm going to say the following. So, multiplying by 1 minus q, so how to extract out of the algebra GQs the actual dt invariance. Multiplying by GQ, that's a separate thing which I don't think I will discuss in detail. If you want some time later this week or next week, we can discuss it on a different occasion. So there is some action of the Weil algebra. So it's PQ minus QP equal to 1. So an algebra of polynomial differential operators and the line. So there is the action of Weil algebra on everything here, on the algebra AQ, on the algebra GQ. Somehow the fact that GQ is of this form, that you have these chains of things, this comes from the Weil algebra action. So in fact, all the generators, they are so the multiplication. So well, one of them, it doesn't really matter who, P, let's say, acts freely, and so it's this creates this change of things. And to get the beginning of these chains, you just need to take the kernel of Q. And this is a simple algebraic argument that is just there. And the presence of this Weil algebra is, in a sense, also hinted at by the vertex operator nature of the story, because in the vertex operator story, of course, you do have the Z and D over dz acting on these currents, so it's not very surprising. Now, what I would like to say, at least hint at, is how to show that these algebras are Koszul. And it turns out that, so what I just raised again, it's in particular using the PBW basis method, we know it for all one vertex quivers. And somehow I'm going to explain to you quickly how to reduce everything to one vertex quivers. And here somehow comes the wonderful story of which I learned about it by reading the papers of Piotr with his colleagues, and about this linking and unlinking for symmetric quivers. So somehow there is this. So if you have a symmetric quiver and you choose two different vertices A and B, then you can well, if there was at least one arrow between those vertices, you can do the unlinking, so create a quiver with one extra vertex, where between A and B you have one vertex less, but the new vertex is somehow created in a funny way with what you had. Linking is something, well, it still adds one extra vertex and it creates one new link between A and B and some other links. And the remarkable thing is that the Mativik generating series of Q is related to the Mativik generating series to these two guys. In both cases, it cannot be exactly equal because you have more vertices. You have, so both here and here, you have one extra variable. And so you need to make some substitutions instead of these variables. And it turns out that you substitute some very simple monomial in everything else, and you get back the Mativik. So there is some kind of invariance of the Mativik generating series under linking and unlinking. And yeah, so when I saw it, it was this result, I was very, very excited because it really felt like it was, it should have some categorification, some meaning on the level of algebras that we consider. And so then one thing one thing I understood sufficient quickly how to categorify linking, so by some sort of filtration argument and answer, but with unlinking, I'm completely stuck, and so I decided to organize a little workshop in Strasbourg to understand these things better. And so, and it worked out very nicely, because by the end of that event in Strasbourg, we more or less knew how to do it, thanks to a great suggestion of Peter. So let me say very quickly what the story is. So you have so let me write this thing. So in the algebra AQ, you have this relation. So this is the derivative of order b minus 1. When you unlink, this relation disappears. And so what does it mean that this relation disappears? How to, so there is a new vertex. So for the unlinked quiver, there is a new vertex. One of the arrows from A to B disappears. So in my algebra, I have fewer relations, but I have a new vertex. How to connect these algebraic phenomena? I would say that, so I have this, so here I have new vertex, let me call it star, so now I have this current E star of Z, and let me say that, let me write it here, and let me say that there is a differential so now so here I am considering algebra for the unlinked quiver, so this element is no longer 0, but in this algebra I can at least try to say that I define a differential which operates like that. Of course, you need to check something. You need to check that it's compatible with the relations of this algebra and so on. But trust me, it is. It's something that one can check. And so, of course, when we have a differential, our first instinct is to compute homology of differential. That's what differentials are made for. And of course, in the homology, this relation will become, again, a relation, because it's in the image of the differential. And then the question is there anything, so what is the homology? We know that so this more or less shows that in homology, in some sort of in degree 0, you have precisely the algebra, the original algebra AQ. But maybe there is something else. But it turns out that the homology of this unlinked algebra with respect to this differential is precisely AQ. And that is the main ingredient of the proof of, so I mean, this is something that needs to be proved, and for some miraculous reason, and that's the ingenious suggestion of Piotr during the conference, to prove that, you need to remember that there is also linking, and start using linking and unlinking simultaneously. So that's what I really like about this story. But once you prove this, how do you proceed later on? You use the procedure that, again, I guess was invented here in Warsaw of diagonalization of a quiver. So somehow, if you have an arbitrary quiver, you can start unlinking things step by step. And then you do it. Generally, you have to do infinitely many steps, but after infinitely many steps, your quiver falls apart into just union of one vertex quiver with several loops. But infinitely many of those, but well, it's price to pay. Then we know that for all of them, the corresponding algebra is Koszul. And then somehow a little algebraic argument shows that you can assemble all these facts together and using this fact prove that AQ is Koszul for arbitrary quiver. And that ensures that all algebras are Koszul and ensures that this method of computing the DT invariance actually works. And I think it's a good moment to stop.
Okay. Questions?
What categorification of linking you just want?
Yes. So in the case of linking, so you do the following. So you look at the current EA of Z, EB of Z, derivative of order MAB, which is not zero. So it's the first of non-zero guy in AQ. And let me call this current for a second maybe C of Z. And then you introduce a filtration saying that all the generators of your algebra are in degree one in the level one of the filtration. And all the Fourier coefficients of this current also now in filtration level one. And define a filtration out of that. And then you take the associated gradient with respect to the filtration. What happens when you take the associated gradient? Since this guy is made of, so you have C of Z, which is equal to this quadratic expression, in the associated gradient, this quadratic expression will become equal to zero. And so you create one extra thing, and so the associated gradient of AQ with respect to this filtration is isomorphic to AQ linked. That's the categorification of linking.
Is there a, so you mentioned, so this equality of Poincare series, is there a, I don't know, maybe like a filtration on AQ whose associated gradient is HQ, or like what's the relationship between AQ and HQ? As algebras say, or is there one?
That is a very good question. That is a very good question. No, I mean, I don't necessarily expect to have any reasonable relationship. So this is, as I was telling you, so this equality of Poincare series, it's some kind of, it's a bizarre phenomenon which is related to the fact that the rational functions representing an honest power series and the Lorentz series are closely related. It's sort of, it's the calculation that you need to do along the way. It's the kind of calculation that would prove that it would prove something like that, right? Because, you know, it has the power series part, which is 1 over 1 minus q. It has the the negative part, which is Q inverse over 1 minus Q inverse, and then you add these as rational functions, and of course as rational functions they add to 0, right? But it's yes, I cannot really give you a very convincing relationship between AQ and HQ as such. So the relationship which is there, and that is the vertex algebra story, that's my work with Sergei Mozgovoi, is that if you consider the Koszul dual, excuse me, yeah, if you consider the linear dual of the homological whole algebra, so the linear dual is a co-commutative coalgebra rather than the commutative algebra. Again, the Kocha, thanks to Yefimov, is free, so that dual is co-free. And that thing turns out to be universal enveloping algebra of something, and that something is the less clear negative part of the coefficient algebra of the free vertex Lie algebra for locality that we discussed earlier. So the meaningful relationship is a relationship like that. So, but relating Kocha itself to any of this, I don't think there is any good reason to expect something of this kind.
Maybe I have a question. So you mentioned that it is possible to view Koszul duality as categorification of division. And can, I don't know, both of you or any of you explain me how to think about it?
Well, I mean, you have this kind of formula, right? So you can
Okay, yeah, I can see.
compute inverses of, at least of something, inverses of generating functions.
Mm-hmm. Okay.
Yeah, that's really all it is. I mean, like dividing by the sort of graded dimension in your algebra is like tensoring with the Koszul dual, or it's like applying the Koszul duality functor.
Yeah. So I mean, if inverting power series seems a little bit far-fetched, then you need to do Koszul duality not for quadratic algebras, but for quadratic categories with finitely many objects, and then you will be able to invert some matrices, thanks for the same reason. So it's
Okay, thank you. Other questions? If not, let's thank Vladimir for the whole series.